long-range Sturm-Liouville operator. There's a word missing. This will not be usual self-adjoint operators, of course. And this is a joint work with Michael Levidin, which should appear soon on the archive. So that the talk is going to be structured as follows. There will be general introduction, very generic setting, and then we're going to make a very specific problem inside this very generic setting and analyze this problem, see what's known about that, and what we found out new about this problem. I will not really outline the proof, I will just give the main elements of the proof. So what are the core elements of the proof and why they are important and what is missing to generalize these problems, and I will ask you some question about the problems.
And you will expect the answers.
Yes, of course. I'm here for this. We need answers. So the main setting of this work is in the linear operator pencil class. These are just operator of the form A minus lambda B, where A and B are two operators, in this case self-adjoint, acting on the same Hilbert space, and lambda plays the role of the spectral parameter. If you think about B being the identity, it's just a standard spectral problem. In this case, B is not going to be the identity. And if you take A and B just to finite dimensional matrices, then this is the generalized eigenvalue problem that often appear in applications. Here we are defining the spectrum as the set of value of lambda for which this A minus lambda B has no bounded inverse. Now, there are some easy cases. If B is sign definite, or A is sign definite if you want, then you just can reduce this problem to a standard eigenvalue problem. And if A and B are self-adjoint, then there is no problem, spectrum is real, you can use standard theory. Now when, it's not working. Okay. When B is invertible, and let's say not sign definite, none of them is sign definite, but when B is invertible, then you can invert B and study this new problem that in general could be not self-adjoint and see what the spectrum is. And in this case, when it's not self-adjoint, it may be non-real. Now the point is that when both of them are sign indefinite, it often happens that actually complex spectrum appear. And understanding how this complex spectrum behaves, especially if the two operators depend on some parameter, is still quite wide open problem. There are few examples that are studied. In some of them, it's seen that it's very hard to say anything. In some other, you see that you can make, seems that you can make numerics, but then everything is more or less hand waving, and there is not much behind. But there is a huge theory behind this. So this theory for operator pencil that I think started in Soviet Union. I think the name was given somewhere in Russia, and then I couldn't find why they're called pencils. But there is a big theory behind this, and there have been methods developed in the last 70 years, but still there are a lot of open problems. And we are going to focus on a very particular problem inside this setting. So we are going to be much, much, much less general. So let's first take the basic operator that is underlying all the rest of the talk. We define T to be this simple Schrödinger operator. Let me write here for later. This is minus Laplacian plus some potential, and this is now on a 2 of R. If the potential of these properties is bounded, goes to 0 to infinity in some particular way, then this operator is self-adjoint, this limit point at plus minus infinity, everything is known. So you know that this has continuous spectrum from 0 to infinity, and it has discrete spectrum accumulated to 0. And that's why we want this class of potential. It was a sum-indefinite operator. And this guy has something in the positive real line and something on the negative real line. Then let's see the second part of our operator. Let J be the sign of X.
Can I go back?
Yeah.
So what class of operators are?
Is minus Laplacian plus
Yes,
V,
yes, but
where
what
V,
about V?
V could be, for example, one V of this kind, let's say V alpha of this kind, 1 plus absolute value of X to the alpha for alpha, say between 1/2 and 2, this would be in this class.
I understand, but you have some conditions. I'm asking a stupid and trivial question, actually. I simply want to understand what they want to say. The limit is 0 and then lim sup of x squared.
Times v is minus 1/4.
So
It's a negative potential that makes a small bump below the real axis. If you want a picture, these are potential of this form. Let's say, in this case, it's symmetric. So you have something that is free here. For positive energy, you have something free, you have continuous spectrum. And for negative energy, you may have discrete spectrum.
It decays slower than x minus 2. That's the point.
Less than a short range, yes.
But if the limit is 0, then it does decay slower.
But
if
x
the
squared
limit
v
is
of
zero-
x could be minus infinity, for example. Go to minus infinity. Take v of x to be 1 over 1 plus absolute value of x.
You mean minus.
And minus, yes, there is a minus missing.
Yeah.
1 over x cubed is not good
Yes, 1 over s
because
cubed
the
is
limit is 0 at infinity.
So we want to
Oh,
take
you
operator
see.
that have discrete
Sorry.
spectrum that accumulate at 0.
I said I'm asking a stupid question.
That is minus 1/4.
You don't want too fast.
Yes, I don't want to fast decay. I want to have a
Okay.
discrete spectrum that accumulates to 0 from the left.
Sorry.
And this is, if you remember what we defined to be this curly A, the pencil, then we can imagine that we have A minus lambda B. This guy here is going to be T. This operator. Let's consider this operator. This is the sign of x, so it's plus 1 if x is a positive number, it's minus 1 if x is a negative number. This is a multiplication operator by sign of x, and then we think to b is this j. So b change the sign depending if you are on the positive real axis or on the negative one. And then we take our operator pencil to be a minus lambda b, or if you want, we just multiply by b minus 1, and it's we consider an operator of the form JTV. So it's the sign of x times minus Laplacian plus v. This will change, flip the sign of the operator when you are on the negative real line.
And why this choice? I mean, just to try?
So no, this choice actually it's present in the literature. So it's the prototypical example that they are using to study this kind of operators. And it's more or less one of the few in which you can do explicitly things, and there is a series of literature from 2007 until last year in which they try to understand, people try to understand, at least in this special case, what one can say. So it's a very special case, and our motivation comes from actually these papers. I'm going to cite them very soon. Just before going there, this gives a non-self-adjoint operator on L2 of R, but it has a lot of properties. So you can think of it as J self-adjoint or a self-adjoint of this on this crane space. But this is not standard self-adjointness. This space here is not Hilbert space. You have a scalar product that contains a measure that changes sign. So there is theory that has been built to study operator of this form, and this operator is particularly nice, has all the nicest properties you would like to have in this theory to study what's going on. Now the point is that people have taken this example and started studying. They made general theorem. In the general theorem you can say nothing very specific, not even say when you can have or not have discrete, like this complex in the complex plane, when it's finite or not finite. So people moved to a specific example in which they could say, at least do things by hand. So build things up and see what happens. And this is the example here. So you take this A minus T minus lambda j, and then you can prove a lot of things. You can prove that this operator is well defined on the Klein space with this scalar product. And you can prove something on the spectrum. You can say, but this is easy. The spectrum is symmetric with respect to the real axis, and if the potential is even with respect to the imaginary axis. So you can just focus on one quadrant or two quadrant of the complex plane. the absolutely continuous spectrum becomes the full real line. So this changing sign take the 0 infinity even to minus infinity 0. Complex eigenvalues have finite multiplicity. There is at most one accumulation point at 0. And at least one of these four things happens. So the eigenvalues could accumulate to 0. There are embedded eigenvalues that could accumulate to 0. There are embedded eigenvalues on one side or the other side of the real axis that accumulate to 0, or you have a finite order of growth of the resolvent near 0. Now the problem is that in this huge amount of paper, they couldn't find a way to say, with this potential or this other potential, you have this or that happening. So you don't know which one of these four is true. You know that there is at least one. There is not yet a way to decide which one of those. You don't know if there are a finite amount of eigenvalues in the complex plane or not. And in a couple of papers, one in 2008 and one in 2013, Bernd, that is one of the main people behind this problem, and his collaborator, they just give some numerical example and say, okay, we have this open problem. We could prove that there is a lot of structure in the spectrum. We don't know how to decide which part of this structure is really there. And if there is some regularity or in which way the eigenvalue, if there are, accumulate to 0. So a few months ago with Michael, we decided, okay, let's see if we can say something, at least on the example that they analyze numerically. So they take as potential like this with alpha equal 1. So we have minus gamma divided 1 plus absolute value of x. This is long range. The spectrum again is infinite. It's accumulated to 0, and T gamma with this potential is a quite well-known operator. If you take this and you plug it into Mathematica and you ask, okay, can we find the eigenvalues of this guy? Forget about the circle on the left for the moment. You find that the discrete spectrum of this is actually given by these red points, red diamonds on the picture. So this is the complex plane, real and imaginary axis, and the complex diamonds are the eigenvalue for this operator A gamma. This guy is V gamma. And this is A gamma. So you can compute numerically. Up to this point, we don't know if there are all of them, what they look like or anything, but you can take them into a computer, hope that the numerics there it's fine and precise, and then you would see a picture like this. And you look at this picture and say there must be a curve that crosses all this point and tell them how to go to 0. And the first time we did it in Mathematica, we plotted the curve like x to the 3/2, and it worked. It was precise. We were looking somewhere here, and it was crossing precise the first eigenvalue. So it's the curve. Then we plotted all of it, and it was completely somewhere else. But still, we were sticking to the fact that there was a curve. And in fact, what we prove is that the eigenvalues of this A gamma for every gamma lie on a curve that is, the imaginary part is some constant gamma, constant with respect to, so some constant epsilon that is constant with respect to gamma, times the real part to the 3/2. So the curve is actually really x to the 3/2 plus lower order, and this is asymptotically as the absolute value of the eigenvalue goes to 0. And this constant is very specific, very precise, depending on four Bessel functions. And it's not just, so the thing doesn't end here. So there is a curve. This eigenvalue all lie on a specific curve with a rate of convergence of mu to the 3/2. But if you take the eigenvalue of the operator T, so let's define T sharp of gamma. This is the operator 3 restricted in a 2 of a plus with sharp boundary condition means conditions at 0. we take t, we restrict it on the half line, and we add Dirichlet or Neumann condition at 0. So you take just the half operator and you put some boundary condition. What you find is that you can take, and this discard the eigenvalues of the Dirichlet or Neumann operator. You can take each of these eigenvalue and map it in a lower order neighborhood of these points. So you can actually identify the new the eigenvalue of the complex eigenvalue using the real eigenvalue of the operator on the half line. And again, the formula is similar. So you get that if we focus on the first quadrant, every other quadrant is by symmetry. Then we find that the complex eigenvalue of the operator A gamma in the first quadrant are either the discrete the positive part, so the absolute value of the eigenvalue of the Dirichlet operator, of the operator with Dirichlet boundary condition, plus a constant that now depend if you take Dirichlet or Neumann boundary condition, times the same eigenvalue to the 3/2, times lower order, or equivalently the Neumann plus different constant lambda to the 3/2 plus lower order. And these two constants have the same imaginary part, they just differ at the real level.
Well, you said there is a curve.
Yes.
There is a asymptotic. So
This is an asymptotic curve where the eigenvalue lie.
but it's not necessarily a curve.
It's not, if you take it all, it's not necessarily a curve, but asymptotically they lie on this curve. Yeah, asymptotically, everything is asymptotic. And this is the same, you have, these are asymptotically described in this way, but you have lower order correction. And if you want to see it in a picture, and the constants are actually relatively simple to write down. In a picture, that's what happened. The diamonds are still the eigenvalues, the complex one. And then you have the Dirichlet and Neumann eigenvalues, and then you map them on this curve here, just forgetting about the lower order correction. So you take just the first two terms and forget about the rest. And this is what you find. They are sandwiching around the eigenvalues. And this distance here is lower order correction. So asymptotically they will converge in the same, to the same eigenvalues. So indeed, there is a way in this which this eigenvalue asymptotically go to 0. And then you can vary gamma and see how this vary. Each color here is a different value of gamma, and you can get a picture of how the spectrum change with gamma. We cannot go too much close to 0 or to infinity because then the limit is singular, but for each finite gamma, you can see how this spectrum varies and how the eigenvalue move around. Now, to prove this result, we need an intermediate result at the classical, in the level of the operator with Dirichlet-Neumann boundary condition. This was quite surprising because we thought that everything was known about this. And for that, we needed to define an unusual function. We need to take, if you look at this formula, there is arctan here, and there is, here is no more arctan, imagine. There is an arctangent involved. Here it's fine, standard arctangent, Q is a regular function. But when you look at this problem here, at the Schrödinger operator on the half line with the Dirichlet-Neumann boundary condition, and try to replicate this theorem, arctangent appears but is wrong. The arctangent will be of a function that is singular and jumps a lot. And their tangent will be their orange curve, but shifted to be always between minus pi alpha and pi alpha. Now what happened is that the formula for the Dirichlet-Neumann eigenvalue to the second order look like this, look like first order term that is well known since ages, plus a second order term that is, roughly speaking, is the arctangent of this function here. But if you take the arctangent, the standard arctangent, each time you hit a singularity, you lose count of one eigenvalue. So you go back and you count the previous eigenvalue. So you need to make this arctangent continuous for all these values, and you need to balance the loss that you get when you do modulus pi alpha. So each time you have a jump, you subtract minus pi to make it continuous. And then what you find is that the Dirichlet-Neumann eigenvalue for the operator on the affine have a very specific, well, you get the second order correction for this eigenvalue in terms of this continuous arctangent. And it was quite surprising that this disappeared when you go back to this problem. There are cancellations, so the two combination, the things that you have to add for both Dirichlet and Neumann multiply and then subtract, and then they will disappear. But yeah, this is, and in principle you can use the method to get as many terms as you want. It just becomes as nasty as you want. But yeah, this is intermediate result. So we have that that is the eigenvalue for the self-adjoint problem of the affine have an expansion at the first and second order of this form, where theta you can imagine as an arctangent, but it's counting these jumps. Well, this is just a picture of what this approximation looked like. So if you take the approximation with the jumps and you consider the m function to find these zeros, you find that the approximated dots already, when lambda is not too small, match very, very precisely with the zeros of this m function. But this is not important. Now, I have not yet told how we solve this problem and how we get these formulas, but you can modify slightly the proof and get much nastier computation and do exactly the same for a potential that is not symmetric. So instead of having one gamma for the full real axis, a potential that is the same on the left and on the right, you have two different gammas. It becomes discontinuous, it becomes non-symmetric, everything holds absolutely in the same way, just more complicated. And then you find that the eigenvalue lie on two different curves, on the left and on the right. And the curve on the left depend on at the first order depend on the constant on the right. So the constant for the positive real axis will decide what is the flatness, well, how small is the constant on the left, and vice versa. The gamma for the negative real axis will decide what's the constant on the positive real axis. And then if you take the two gammas to be the same, you get the same picture as before. Now, we found the curve, how we did it, and why we used this problem, because how we did it, it's really why we used this problem. When you take this potential, V gamma minus gamma 1 plus x, everything is explicit. And that's the only way we could do that, sadly.
So for any other alpha, you cannot do anything, right?
For different alphas, no. So if you take 1 plus x to the alpha, no, and this is the open problem of it. Look at the end, and they will explain why. So first of all, there is
alpha is
now alpha here is 1,
One?
so there is no alpha here. But if you take potential with different decays, we don't know what to do.
But your condition was that the lim sub of x squared times v of x.
Yeah, this is fine if you take absolute value of x.
Because
This
it's
is 1 over x at
minus
infinity,
infinity.
so it goes to minus infinity.
Which is less than minus 4.
Is it?
Yeah.
That
Substantial.
might seem like bigger.
Yeah, but why did you start with this general condition in the beginning when
Because
you
we
were
hope to
specializing?
actually go back to that general condition at a certain point.
You ought to.
Yes, I would like to. We just don't know yet how to do that. So we restricted the theorem that I've shown you by Burns. This theorem here holds for all potential in that class.
I see.
So at least the abstract structure of the spectrum is the same.
But B is supposed to be self-adjoint, right? For the theorem. B is supposed to be self-adjoint.
Yeah, for this theorem we get A is this operator with any V in the class that I said at the beginning, and B is always sine of x.
Can you
So it's the senior,
what is D in this case?
is this sine of x.
For
It's
Sine
minus
of x.
1 for negative x and plus 1 for positive x.
So that the theorem of these guys are for that.
This is for this particular A, where we take A to be j times tv. So where this operator B is the sine of x, the chain flip sign on the left and on the right, and A is the Schrödinger operator of this form on the real line. And V is one of the potential of the class.
And since you consider non-symmetric V, Maybe you can consider non-symmetric B as well.
Oh, this could be, but already giving it for this B would be something. If you take non-symmetric B, well, as long as in non-sign indefinite, then probably something similar happened. Just this theorem holds for this. If you modify it, it should be similar probably, but it must be reproved. And for V in this class, these are all true, but you don't know if the spectrum is finite or not, the complex one, for example, or which one of these four points holds. You know that one of these things happens, but you don't know which one. And it could be more than one. It could be that there are embedded eigenvalues on both sides.
But numerically, you can put mathematically any of this.
Not really, because the numerics of this depend on what I was going to say. So you can reduce the problem of this form, A gamma equal mu, with any potential in principle, to a problem of finding the zero of an M function. Either in the determinant form, like here, you take operator on the half line, you look for your solution. These are the solutions that are in L2 when your eigenvalue is in the upper half plane. And then you rewrite matching condition at 0 using this your solution on the right and on the left. And you end up having either a determinant of this form, so first derivatives times the function on the other side, plus first derivative on the other side, plus the function computed at 0, they must give you at 0. Or with quotients, phi prime over phi minus mu plus phi prime minus mu over phi mu equals 0. And then you need to find the 0 of this function. Now, to find the 0 of this function, you need to know something about this function, and you need to know something for 0 energy. And that's very tricky. In this case, we are lucky because for that particular potential, everything can be rewritten with hypergeometric function. You take Kummer hypergeometric function, there are many appearing, then you start using recurrence relation, you end up with 4 functions. And these are the 4 functions that are written here. So you get a hypergeometric function with first coefficient that diverge potentially everywhere in the complex plane, second coefficient that is either 0 or 1, and the third coefficient that goes to 0. Now the serious problem is that this function here is extremely unstable. So depending on how the parameter are, the ratio of the parameter and where they are moving, they could do absolutely anything, and they oscillate very, very widely, but at least it's explicit. You know that this is a special function. You need to control the behavior for small mu in the complex plane very accurately. But you have just one explicit function, or 4 of them. And this is not easy. I mean, here you see the function and our approximation, they match very, very nicely, but these functions are oscillating and we are far from 0, quite seriously and with pretty big values. Now, we have been lucky because there is some uniform asymptotic for this function for real parameters. And when we wrote to the authors of this uniform asymptotic expansion to ask if somebody did the complex case, luckily we did it before trying to prove it ourselves, we found out that there is a book that is going to be published now, actually I think it's in press now, in which Nico Temme did exactly what we were missing. So there's the uniform asymptotic expansion for this guy in the complex plane. And he sent us the draft of the chapter with this expansion. And this is essential. So you need to do, if you want this, a very, very careful WKB with close to 0 energy. And then you have the integral of an exponential that the singular point that are going to collide when our parameter gets small, and then you need to find a change of variable to treat this coalescence of singularity and find out what's really going on. And in this case, for this special range of parameter, things are nested to compute but get fairly simple. So you get some prefactor that is in common, that gives some, now A is 1 over square root of mu, so it's a big parameter. You have something that is damping when it's C is 0 or not present when C is 1 times some oscillation that are in common, so we don't care. And this is multiplied by a function that includes this cylinder function of this form, cosinus of pi a j nu plus sinus of pi a y nu, times some coefficient that are small with respect to a, so that you can control with effort, but explicitly. And then you can reduce this. First of all, you can take this. You can take this determinant, replace the phi mu with the appropriate hypergeometric function, and then ask Mathematica to compute it numerically. And then you see a picture similar to the one above. But as soon as you start varying gamma, it just cannot do it anymore. So if you imagine this as being the charge, if this guy is smaller than 1 or bigger than 3, the numeric it just doesn't work because of the oscillation of this function. But again, we can use the asymptotic expansion of this form, and then we compute asymptotical solution explicitly. So we can take the Dirichlet problem, set our Jost function to be 0 at 0. We get some very nasty equation, but this equation would be in the end the cosinus pi a of j nu plus lower order term plus the sinus pi a of y nu plus lower order term equals 0. And that's where the arctangent comes from. You get a tangent there, you show that all the lower order terms are nice and regular, and then you get the formula of the type that was above. And for the Neumann equation, it's similar. For the operator A gamma, it gets much more complicated, but the idea is similar. You have this huge determinant, you should find it 0, and you know how to control each term asymptotically. Then you start transforming the hypergeometric function one into the other. You start using the relation between Bessel function to reduce their number. You prove that they are regular in the appropriate quadrant, and you end up having an equation in terms of tangent of pi a equals something related to the Bessel function, and this is what's giving at the end this arctangent. And in the middle of the proof is crucial that one say, okay, let's use the ansatz mu is equal to lambda plus some constant lambda to 3 alpha plus lower order. So you replace explicitly your ansatz, and then you found that the lower order are really lower order, that the constant is really constant in lambda, and that you can reduce everything to a form of this type, and this guy here have the same imaginary part. So this theorem here actually, when you consider the absolute value of the imaginary part, hold with the unique constant up to the first order. But the real core of the proof, what happened here? I don't know.
How did you manage to?
I don't know. It just rotated.
Question is what we are going to do.
Okay, but we can read the one before.
That's what happened, it's not self-adjoint.
Yes, you see, it's self-adjoint.
Because of that, yes.
But I mean, if you use schema,
Myself,
you
myself,
don't
adjoint.
even know how to do that.
So using this this method for the Kummer hypergeometric function and finding that we have this everything in terms of this cylinder function is really the core of the proof. As soon as you get that, you can use this theorem of solving the transcendental asymptotic equation, control the errors, and you get the result. Now, this is where the serious problem comes from. If you want to tackle the general case, so you want a potential in the class that I said at the beginning where there is any alpha. What you need to replicate what has been done for the hypergeometric function. So you need to take your solution and be able to control this solution when the energy goes to 0. And you need to be able not to control just the first order of them. You need at least the first order with very explicit control on the oscillation. Because what's the core here is that we can see how this oscillates when gamma over 2 square root of mu diverge. So there is this cosinus and sinus that really encode all the oscillation times the Bessel function. And one should should do the same for the generic potential. And moreover, it must be uniform in the argument of lambda. So you must be able to go to 0 wherever, however you like, and still have some control on this, on its behavior. Now there is a result, we have been asking around, there is a result, this by F5 in 1982, and this is the scattering, the low energy scattering, something like that. But the problem are, first of all, he gets only the first asymptotic term, the first term. This is a problem, yes and no. The proof works in this way. He gets the Yost solution solving a Volterra equation, and then taking iterates of that. And then you just take the first order and control that the second order is small, even if you do some complex perturbation. Probably working hard enough on that, one can get the second term. Now, a more serious problem is that this estimate gets explicit enough only when the potential is short range. So when the power alpha is bigger or equal to. And we need alpha to be between 1 alpha and 2. So 2 is really the threshold. Things are not nice. We don't want that. So the technique of F5, the result of F5 are nice when the potential go like x to the minus 2 or faster at infinity. So it gives nice result only in the wrong range for us. And then finally, the really serious problem is that in the proof he has to remove 2 cones around the real axis. And in our proof, we really need to touch the real axis. So we need to get points that are on the real axis and points that are on the imaginary axis and that move around the complex plane. So the very hard part of the proof would be, how can you remove this requirement? And this, I've been trying to remove this limit. So at least having the same, so not explicit for wrong alpha, but at least remove the condition that you cannot stay too close to the real axis. And that's really not sure how it can be done. So you need to control this Yost function everywhere close to lambda, not just outside some cone.
But this is a natural assumption because he's doing scattering theory.
Yes.
And you are somehow doing.
Yes, the problem is that you need to start from the condition at infinity. So you ensure that you are decaying at infinity and then you go back to 0. Maybe you can do it the opposite way, but I couldn't make it work yet.
What is the big conjecture?
The big conjecture is that there is a picture like this for all the potentials. And I don't know if the power is the same. There is a certain curve where all the complex are very linear,
coming closer.
and there is a range of powers in which the picture looks the same.
So you can exclude certain domains, it will be no eigenvalues there.
Yeah, but then, for example, are all power of 3 halves? Or this depends on alpha?
When alpha is bigger than 2, presumably.
There should be nothing, because in that case
You get a finite number of complex eigenvalues or something?
so there could be finite number or there could be nothing.
And there is no conjecture how the power depends on alpha, right?
No, there is no conjecture because there is.
You know it at one
You
point.
cannot even draw this picture. If you try to draw it with taking a numerical solution, it just doesn't work. So it's not, and the really hard part is control what happens at 0 very close to the real axis. So trying to understand for energy 0. Because as soon as you get that, you can plug in this, you can take the determinant, start to control the errors and get to a result of some similar form. Maybe it's not arctan, it's something else. But this is a real problem. You cannot exclude this neighborhood. Then okay, that's true. He was doing scattering, but at least his method was able to go to 0. And in this case, you need to mix both scattering, because what happens is that you are relating the scattering solution on one side with the bounded solution on the other side, and vice versa. So you need to take both from the scattering and the bound state analysis in both directions. So if you get any suggestion on how to solve this part, I will be very, very happy. But yeah, that's it. That's the question. Well, they gave this problem. Is there an irregularity, and are these eigenvalues really there? At least in the example that was in the paper, we could prove that there are, and they are lying on a special curve. And we can see where the problem are, so where things get nasty. But then we have not yet been able to go deeper than this. So take any potential and see what happens. What definitely is true is that you need some negative eigenvalues and something positive to get the sign indefinite potential. As soon as it's sign indefinite, you don't have, nothing happens. If you take Laplacian, there is nothing in the complex eigenvalue.
Are there actually results like this in the discrete setting? So take the discrete Laplacian and you take some sign operator and...
Yes and no, it's not really the discrete setting, but there is a paper by Michael and Brian Davis in which they consider a 3-diagonal matrix plus a signed B. So you have diagonal that is sometimes +1 and sometimes -1. And then they study a similar problem. This has appeared last year, and in that case the situation is completely different. You have complex eigenvalue, and when you move, if you put a strength in front of one of the two operators, when you move the strength, the eigenvalues start oscillating and jumping around below some specific curve.
But what if you just, I mean, really do the same? You take the discrete Laplacian, some potential that decays, and some operator that's multiplied by something that's -1 here and +1.
Explicitly for this operator, there is not. There is this similar setting at this operator pencil considered by Michael with Brian Davis that are, if you want, different but in a similar fashion. You get to sign indefinite operator, one of which has the form of a Laplacian, discrete Laplacian, say a copy matrix, and the other that is just diagonal. And then the structure of the spectrum is
So you're
absolute
saying
madness.
there is, what is exactly the structure? So there is no potential, you say, in this case. So because
In this
the
case,
tridiagonal matrix, so you have it's basically a
Yeah, and
discrete
you-
Laplacian, and then the diagonal is the potential.
yes, and you use a potential that is +1 in some part and -1 in the other parts.
So basically,
And then,
the B is 0.
Yes, if you want, yes. And just depending on how these plus and minus are put and the strength, they have different picture about the
But it's a finite matrix, so you have
And
boundary.
then you send the dimension to infinity and see how it evolves.
But this will, now how do you get it non-self-adjoint now? You still multiply by something.
You're doing something I maybe wrong. You have this Jacobi matrix here,
Yes.
minus lambda, this this other matrix C.
So that's what you mean.
here.
So this, and this one is something that changes sign.
Yes, both of them are not sign definite, and you look.
Yeah, okay. But no, but I mean, if you change the sign more often, then this is a very different problem, right? And
Yes.
in the continuous case, so that's why I
But
say
what they do here is like you change sign only once. You have -1 and then all
Oh,
ones,
okay.
and then you have 2 and the other. Then you mix them up. They have a full zoo of cases studied there, and that's it gets quite complicated. You see a lot of points in the complex plane that are in a structure like this, and this start bouncing when the dimension change, and everything will converge to be real when you get outside -2, 2. It's slightly different, but the idea is that you want to take a discrete operator that is made of 2 parts. One is a Laplacian and the other one is
Yeah, I
something
would
else.
want have the question of like copying the same problem to the discrete world.
You get a completely different picture, but
Really?
So this is the precise copy of the problem for b equals 0.
yeah.
Yeah, okay, but maybe b equals 0 is special.
No, I think
No, I think you should really try the same thing. You should get a potential minus 1 over 1 plus
the
n,
distance,
right?
and see what happens. Yeah, that could be actually a nice
really
thing to
the
do,
same thing.
to see if something similar.
without boundary.
So is
Mhm.
any self
Without boundary,
Mhm.
you
The foods
with
of
the finite matrix, so you
Yeah,
have a
yeah.
boundary, right?
yes.
so
Then they send the dimension to
is
infinity.
n self-adjoint or not? The matrix.
I think they are.
Because how do you
Separately,
get
but I
complex
don't-
eigenvalues? I mean, if n is self-adjoint and if m is self-adjoint, how do you get complex
Let me
eigenvalues?
let me try to
They're not
find
sign
them.
definite.
They are sign definite. They do not,
They're
not
not.
sign definite.
These
Both
are the
of them.
eigenvalues of m minus 1 times n because he looks at the.
multiplies this over.
So if m is 1, now the question is for which lambda is that not invertible in a bounded way, right? If m is 1, then that would be the spectrum of n, but otherwise, so it's the spectrum of m minus 1 times n if m minus 1.
Eigenvalue is a bad word, no? For this.
Oh, that's what they
Well, it's
do.
the eigenvalue of some operator
I
because
think
it's,
depends.
if at least if b is invertible, it is the eigen. I mean, it is the spectrum.
They use it.
Okay, this is.
I know. But it's confusing.
That's too big. Come on.
I think this is the least thing that is confusing.
So that's the four. Oh, but it's unreadable.
I'm already stuck with this.
This is the form of the matrices. Let me try to find whatever. And the shape is
exactly.
you get a similar.
So you have one half of the answer.
Yeah, in this case it's alpha.
Oh,
well,
okay.
m ones and n minus ones, and the other operator is three-diagonal, and then there should be a picture somewhere.
Okay, so this is now for finite matrices, right?
And then yeah, they take the dimension going to infinity as a certain point. There should be picture. Yeah. Here you see this is a curve bounding the eigenvalues in one
Do you
case.
have the movie that Brian Davis used to show when they how they bounce?
I think you can look it online. Yeah, this is what happens. The things are different. They don't go.
But I think you should really look maybe at these potentials.
But yeah, taking infinite discrete Laplacian and look at potential like this would
Yeah,
happen.
and really the positive definite Laplacian actually. Then adding this
If it's
potential.
positive definite,
No, and then you add the potential, so then it's not.
So you take the other part, not positive definite.
Right, because
But no, if one of them is sign definite, you just divide by random and multiply by square roots, and then you make it standard.
no, but I mean in the continuous world, the Laplacian is positive definite, right? So if you want to like maybe get the same type of result, I think you should really copy the same. So you take the real discrete Laplacian of the adjacency operator, and then you add the negative potential, and then you.
This is
Okay, so
So
here
this
put
is
discrete
what I mean, you
Laplacian,
should, like-
here put discrete Laplacian.
And then maybe numerics may also be easy, and then maybe you can look at these other cases. But the question would be if you get something similar or not.
Yeah, that's actually a good try. I will let you know next days.
yeah.
So here they use Laplacian minus b, and here they corresponding sign.
Yes, and maybe you take the lattice on the half points, right, and you make exactly at zero.
Yes, then you see what happens with the match. Let's see what happens.
I think this should be, at least numerically, should be actually simpler than the continuous.
Marcello, I understand that you explained this in the beginning, that you don't try to come up with a general theory. You just want to see what happens in one specific case.
I would like to come up with a general theory.
Yes, I mean, in the talk that you.
In the talk, I will not
pursue
come
this
up with a general theory.
talk. What will happen is, instead of this step function, when you have 1 minus 1, You kind of, you make it change sign a couple of times.
Like sine of x, or cosine of x.
Something.
Sine
Well,
of
I
cosine of
didn't
x,
mean,
yeah.
I didn't mean to make it change periodically.
But just few times.
Let's say a few times, it changes.
Absolutely not known.
But this is what, I thought about this when you recalled us about this Brian's paper, where they have minus one plus ones in different proportions.
Yes.
They do they mix them up? So that's, I thought maybe if you mix them up, you will have something else.
I think they are, if it's not there, it's, no, in that paper there they show that it doesn't matter if you mix them up. You can always come back to a problem in which they are applied. They have another, I think they're working on the random case. So if you put minus and plus at random, what happens? And this is different. But here, if you put, instead of sine of x, you change in more places. I don't know what happens. And I don't think
And how universal is 3/2?
this would be the first thing I would like to know. That's why I was looking for something like a file, even just the first order, because hoping that, like in this case, the second order cancel and you get the same imaginary part, that would be
Where is this?
enough.
This curve of.
Curve is 3/2.
Curve then, okay.
This curve, where is
Yeah.
it?
Does this come up in any physical problem?
They started from a physical problem. I don't really know about the details of that, and I don't know if it's a reduction of a physical problem. So there should be some connection of things changing sign on metamaterials, but I know nothing about that, so I'm just spitting out words. The
You
first
just say
paper,
metamaterials and you get a grant. That's
but then people ask how, and I don't know.
You get megagram.
So
Meta
in the first paper, in one of the first paper in 2007, there was something about application of this. And operator in Crane spaces have application, but for this particular problem, I don't know. I think it's more of finding a problem in which we can say something and then try to understand how generic is this something. But it's relatively young. I mean, this problem is just from 2007. So they just need a good idea to solve all of that.
That's typical.
This is normally how it happens.
But how generic is TRF? I don't know. It's the first question I would ask for the general one.
And you have this Coulomb potential is, well, Coulomb decaying like x minus 1 at infinity. Why did you take that one? Because it was convenient.
Because it was in their paper.
No, but
It has solution, but it was in their paper.
Dimension 1 should be logarithm 1 should be what?
In the paper with the conjecture, they use this as a special example for the picture. So when we start, we said, let's see at least if we can say something about the example. And then we suffered and we said something. Then we said, let's see if we can make it more general. And then we are still suffering.
So, okay, so it's work in progress.
Yeah,
Okay.
this part here will be submitted without the general. So with the question, what happens in general? What's the exponent?
I mean, concerning the question of the application, you have some models where you have a divergence form operator, and the symbol in the middle is something like your J, which changes sign. Okay, so you have on the one side something like a positive Laplacian, and on the other, and then you have a transition where the symbol becomes negative. And then again, you can solve it in the one-dimensional case. This is being done by work by Vadim Konstrikin and some other people. Again, because you have explicit control in the one-dimensional case by ODE techniques.
Can you
But
give
there
me the
you
reference?
look at the eigenvalue problem with the sign change potential.
So there's
You
no
don't-
potential. It's like you have a divergence type operator, and you
Yeah.
have in the middle kind of a matrix A, and this is typically elliptic if you have elliptic operators, and here you have something which changes from something positive definite to something negative definite.
But it's always definite, either negative or positive, right?
Well, you can argue what happens at zero. You might have a smooth transition where everything becomes even harder, but I think they considered a case where you have something with bounded inverse.
Because as soon as it's no more sign definite, you could get this things appearing.
If there is
I didn't
jump,
know about that.
if the transition is smooth, it's gonna be a degenerate problem. It's a completely different ballgame. I guess if it's just a jump and then on the interface, yeah.
Your case is integrable somehow.
Yeah.
So maybe there's a chance that there's an exact curve where they align.
It could be, yeah.
Not symptotic, but just exact.
This could be. I mean, at least if you look at the picture, you see there must be one. It looks so nice.
Maybe you can do a formula.
You
for
can
that.
always fit a curve through this.
But at least we know asymptotically with that.
All right.
Thank you very much.
It's not so trivial.